Hello, hello, Kristen.
Hello, Professor Griffin.
Hey, Kristen, I pulled up that recording of our morning class,
Yes, sir.
and it's fine. Everything's just perfect about it. So I think you could watch it towards the tail end. We were having trouble with our microphone,
Yes, sir.
but you could watch it and you'll understand it perfectly.
I will go back and do that. I was hoping that this one would come in, clearly for us and everything.
Me too. Well, right now it's working, isn't it?
Yes, sir.
Good. Excellent. Okay, let's see. I need to get this where you guys can see it. Yeah, that's pretty good. I thought we'd review that step-by-step method to solve thermal problems. You guys have seen this before. It's even in your book someplace. Let me see if I can find it. I don't know where that would be. Step-by-step method to solve thermal problems. Wonder what you'd look up. You guys know what I'm talking about? Would it be in chapter 2, maybe? Nice. Let me shop around here. Maybe it's in probably in chapter 3. Yep. Hello there. Let me see who we got on board here. We have Sang, Levi, Kristen, Kerman, Abdullah. Oh, we're doing good. Now, this is on page 80 in your book. Now, I like mine better than theirs. They only have 5 steps on page 80 in your book. But you can look that up and see what they said. The idea is when you're doing thermal problems, there's a method involved. The step-by-step method. And if you're having trouble, why don't you write that down? And if, like on your final exam, it's going to be a take-home open book final exam. If you're stuck, well, get out this list. See, first step is to make a device sketch. We've had different devices. Let's see. So we've had turbines, and we've had throttles and nozzles, and we've had pistons and cylinders. Step number 2, the PV diagram is all important. I've told you it's the key to success in this class. And then later we learned the TS diagrams. They're important too. But without processes, they're worthless. You have to have a process on there or they're no good. Step number 3. Now, step number 3 is the model. Now we have different models. The best model is the tables in the back of the book because they've been checked with experimental values. If you have something that acts like an ideal gas, you can use the ideal gas model. And we have the ideal gas law, and we also have some other equations. Like, for instance, this equation here, delta U equals CV delta T. Did you know that's an ideal gas equation? You can't use it unless you have an ideal gas. It's no good. It's only for ideal gases. Then you've got to know whether it's a control mass or a control volume, because see, the first and second laws are different. If you use the wrong first and second laws, you're going to get the wrong answer. And you all know what a control mass is and what a control volume is. A control volume has mass going in and or out. A control mass does not have any mass going in and or out. And then there's your first and second laws. And maybe other equations. Sometimes problems have some of the forces equations in them. Or what was that thing about compatibility? Yeah, we've had other equations. We had that hydrostatic equation. I don't know if you remember that. How did that go? The change in pressure equals, oh gosh, oh gosh, what was it? Rho GH, was that it? Or
On the first chapter, sir?
uh, let me
That
look it
sounds
up.
right.
I think it's right. Let me look it up.
That sounds correct.
It goes way, way, way back. Back when we were younger and better looking. Yeah, there it is. I got it right. It's on, happens to be on page 15 in my book. So there's other equations besides the first and second law. And then there's, hey, if you just tuned in, I'm giving a short review here about the step-by-step method to solve thermodynamics problems. And if you're having trouble solving your thermo problems, you're probably not doing something that's on this list. Now, number 6 is, are we using SI? That's System International. That's what they used to call the metric system, you know, meters and kilograms and all that. Or are you using British units? Like, for instance, BTUs. See, a BTU is a British thermal unit. And you know what that is. It's the amount of heat energy necessary to raise 1 pound mass of water 1 degree Fahrenheit. That's what a BTU is. But you knew that. And then the last and final step is to check your answers. There's different ways to check your answers. Just go over your math, maybe have a buddy, the two of you together, work on it. I don't know. Hey, look at your answer and see if it's ridiculous. If you get a ridiculous answer, then maybe you did something wrong, huh? Okay, well, there's your step-by-step. It is now 1 o'clock. Class has officially started. All that was free, no extra charge on your tuition. And I've shown you this before. They have on page 80, I think 5 steps. I don't know. They left out a couple. But let me go on and show you something else now. I'll show you something really neat. This whiteboard that my daughter got me, guess what? It's got a reverse side. Let me see if I can flip it over to the reverse side here. Well, yeah, here we go. Let's try to flip this. Yeah, here we go. Now look at that. Now isn't that slick? It's got a reverse side. I didn't even know it did that. Oops. I think it's okay. All right. Now this is more review stuff. We'll get into our today's lesson here in a little bit. What are we studying today? Let me look at my my notes here. We're going to do a refrigeration cycle today. That's on the menu. Refrigeration cycle. That'll be fun. But right now, we are reviewing. Remember on that reverse side there of that whiteboard, there was a step-by-step method. And one of them was step number 5, the first and second law, and other equations. Well, did you know the first law can be written different ways? Look, here's 3 different ways right here. 3 different ways. Control mass, control volume, and transient processes. It has 3 different ways right there. And the second law, guess what? The second law can be written 3 different ways too. This is for control masses. This is for control volumes. And this is the second law for transient processes. Hope you can read my writing there. Let's just talk about these for a tiny minute. I wonder if you can see all that. Not too bad. Okay. This big E here stands for something. There's a 2 and a 1. That's the final and the initial. It's beginning and the end. And the E stands for, you know what that is. That E stands for
Energy.
Yeah, total energy. Total energy, including all forms of energy. Namely, kinetic, potential, and internal. You know, internal energy. See, little u is specific internal energy. Big U is internal energy. And they have tables in the back with little u in it. Guess what? Internal energy depends on how hot you are. Of course, now we're all pretty hot. All of us in our class, we're hot. But see, the hotter you are, the more internal energy you have. Now, kinetic, you know what that is? That's how fast you're going. If you're going fast, you have more kinetic. Potential energy, we're talking gravitational potential energy. And that has to do with how high up you are. Really, we're more interested in the change in these things. You know what that final minus initial is? That's delta E, isn't it? And we're really more interested in delta U and in delta little u. Because the first law can often be written in little letters like that. That's the first law in big letters. But see, we're really more interested in the change in these things than we are in the things themselves. Now, the first law for control volumes, you've seen me write it many times. There it is. I ran out of space here, got lazy. But there it is. You've seen that many times. Now this is the first law for transient processes. Now that M2, that stands for the final mass that you have in your system. And that M1 is the initial mass you have in your system. And there you are. There's your specific internal energy. This term is your specific kinetic energy. This term is your specific gravitational potential energy. This is your heat transfer. That's your work. There's no dot over that. See, if you put a dot over that, you got power. You put a dot over that, you got heat transfer rate. This is just heat transfer. Hopefully I'm boring you and you're getting sleepy now. Probably had lunch and your eyes are sort of clouding over. You're getting real, if yours aren't, mine are. Okay, now here comes the second law. Now notice the second law has a form for control masses, for control volume, and for transient processes. So there you have it. There's the first law, or the second law for control masses. That's final minus initial entropy. Or you could write it as delta big S. There you go. And it's equal to this term here, which is the heat transfer divided by the Kelvin or Rankine temperature at which that heat transfer takes place at the boundary. When you have a system, the system has a boundary, and that's the temperature of the boundary across which the heat transfer takes place. That's your generated entropy. Now you can write this in little letters. That'll be okay. Look here, I'm writing it in little letters. There you have it. And you know some stuff about this generated entropy. If it's equal to 0, you have a reversible process. If it's greater than 0, you have an actual process. If the generated entropy is less than 0, you have violated the second law of thermodynamics. Go to jail, and what do they say in Monopoly? Go to jail. Do not pass go. Go directly to jail. So
Or get a Nobel Prize.
That's right. You'll get yeah, but you will get a Nobel Prize. All right, now on the second law for control masses, control volumes, and there it is for your transient processes. You all know what these are, these transient processes. That's when you're starting up a turbine, maybe, or you're letting the pressure out of a pressure vessel. It's not a steady state process. See, this stuff here, these are steady state equations. That dsdt and that dedt, that's 0 if you have steady state. But transient processes are not steady state. It's like when you start up the turbine. There's no pressure in it. There's no steam in it. You start it up. It might take you a while, a couple hours for the thing to build up, to crank up to the steady state situation. But there it is. And this is your final mass and your final specific entropy minus your initial mass and your initial specific entropy. This is a heat transfer term of your second law, and this is wait a minute, I'm missing something. I think I'm missing something here. Just a minute. Ooga. I'm missing something right in here. Oh, well, we'll stick it at the end. Oh, well, what the heck. But what I just gave you guys right here was wrong without this. You have to have your generated entropy term, and now it's okay. Okay, well, there you have it. We've just spent 12 minutes on just reviewing some important equations. Did anyone have a comment or question before we start tackling refrigeration cycles?
I do have one question, sir, if you don't mind.
Sure, go ahead.
It was over the homework,
Yeah,
and we had specifically it was process 4 to 1, and you had mentioned something on mine where I had a temperature difference on mine or something that was incorrect. I was curious with
Yeah.
the temperature coming out of the turbine.
yeah.
Is it generally going to stay the same at 3 to 4 and 4 to 1?
Okay, now let me find it. Do you remember what problem this was that you're talking about?
106E.
Yeah. Now, I'm grading that, and I'm giving you points for it, right?
Yeah, you already graded it.
Yeah.
I just had a question about what I had incorrect, essentially, just because I had missed it.
Yeah. Let me find it. Now, who am I talking to, please?
This is Don.
That's Don. Yeah. Okay, Don. Hang on. I'll have it here in just a second. And then
I just wanted to know, so in future, future problems, I'll
right.
attack it correctly.
You want to know how come I didn't like it?
Mhm.
Well,
Yeah, just so I can learn from it. And
I want to find it here. I've got it here. We're talking totally organized here. We want 106E, right?
Mhm.
It's
I think,
Inglés, senor.
yes, sir. I think I know. I'm pretty like 99% sure I know what I did wrong,
Yeah.
but I just wanted to verify that that is what I got, what I did wrong.
Okay, just have patience with me, Don.
Oh, you're fine. I apologize for disrupting the flow of the
No,
class.
no, that's what we're here for. Okay, I got it now. I've got the 106E. And you're talking about 4 to 1, process 4 to 1, aren't you?
Yes, sir.
Okay. Well, let's say goodbye to all that stuff. We don't need it right now, but wasn't that fun going over that? It was good. Good stuff. All right, we're going to erase all that stuff. And we're going to try to answer Don's question. Now, Don,
Yes, sir.
from 4 to 1 on 106E, process 4 to 1 is the condenser. And it's not only isothermal, but it's isobaric. It's isothermal, and this condenser is operating at 120 Fahrenheit.
I think that's what I had misunderstood, is because in the problem it said that the turbine had a condenser exit at 120. I
Yes.
thought that there was a temperature change.
No.
Not saying that there was a
No.
there was a heat transfer, but I thought maybe there was a temperature change through the turbine.
At state 4, the temperature entering the condenser is 120 Fahrenheit.
Okay.
That's a state 4. Now at state 1, the temperature exiting the condenser is 120 Fahrenheit. It's isothermal. It's also isobaric. Condensers are isobaric. The pressure at state 4 happens to be 1 point blah, blah, blah.
Like 1.6, I think.
Yeah, 1.695 kilopascals. And the pressure at state 1, where it exits the
PSI. It doesn't matter. I get what
it
you're saying.
matters. Don's on the board. Don's on the board. He got a thank you point. Good going, Don. It's PSI, isn't it, Don?
Yes, sir. I wasn't meaning to be picky.
No. I'm proud of you. It's 1.695 psi. That's exiting the condenser. Are you satisfied
Yes, sir.
with that now? You're okay?
Yeah, I just wanted to verify that that's what I was
Yeah.
thinking. I'll go back over the problem, see what I got it
Okay.
from. But now that I know that that's correct,
Good, good,
I'm
good.
good.
Okay, well, we're going to go on today's topic. I'll put Dawn's thank you point over here in the corner someplace. Today's topic is refrigeration. Refrigeration cycle. How come I put a capital C there? That should be a little c. There you go. Okay. Let me give you the schematic of a refrigeration cycle. Now when you do these schematics of a refrigeration cycle, you want to draw the cycle counterclockwise. And you want to draw the low temperature down here and the high temperature up here. And let's suppose, I'm just making this up because I want you guys to know how to cook this stuff up. Let's suppose this is 30 Celsius and this is minus 10. This is your ice cream here. You want to keep your ice cream at minus 10. Now this right here is your heat transfer rate at the low temperature of 260. And again, now I just made this up. And now watch it. The power has to go in. You have to plug in refrigerators or they don't work too good. The power here is going to be 50 watts. And this is the heat transfer rate at your higher temperature. And it is 310 watts. Now we got to make sure the first law is correct. The first law says that if you take the 260 and the 50 and you add them up, you should get the 310. Do you?
Yes, sir.
Yeah, it works. Good going. Okay, now here's what I want you guys to do. I'm going to shut up now for a couple of minutes if need be. I want you to find the actual beta. They have a name for it. They call it the coefficient of performance of your refrigerator. And then I want you to find the maximum. They have different names for that. They can sometimes call it the Carnot efficiency, or not efficient, COP. But maximum will do the trick. I want you to find those. I'm going to shut up. I want you to find those. When you have your final, you can look them up. There's equations for them. I'll be quiet. Go for it. See if you can do that. I want you, what we're doing right now, if you just tuned in, the students are trying to find actual and maximum coefficients of performance of that refrigeration cycle. Let me mention, if we have trouble with the microphone today, like we did this morning, the recording is fine. I listened to the recording and it's just perfect. So you can pull up our wonderful lecture and it's fine later.
Oh, crap.
Remember, these betas are always bigger than 1. Efficiencies are always less than 1, but these betas are bigger than 1. Well, I gave you maybe a minute or two. I've got the actual beta, and here's what I think it is. I think it's 5.2. How about it? Are you happy with 5.2? I need an out there.
Oh, what's the formula?
I didn't hear an
That's what I got.
What's the
So 2 people got it. Good for you guys.
I got it.
Yay! Do we need to write the formula?
Yes, please.
Okay, let's do that. Now what this is your what you desire. You put it on the numerator, you put what you desire, and the denominator, you put something that costs you. Well, you see, what you desire is to keep your ice cream cold. This is you desire to remove 260 watts from your ice cream. So that goes in the numerator, 260. Now I know it's watts, but they're going to cancel. Now what costs you is 50. You have to pay for this. This power, when you plug in refrigerators, you got to pay the electric company. So you put that in there and divide it. The units cancel. And I got 5.2. Now, how about the beta max? Does anybody get that? We'll pick on somebody. Hey, Daniel, unmute Daniel and tell me what you got for the maximum coefficient of performance. Earth calling Daniel, come in Daniel. Daniel's not coming in. Maybe he hadn't done it yet. That's okay. Take your time. Kerman, we'll pick on Kerman. Kerman, unmute and tell me what you got for the maximum coefficient of performance.
I haven't got it yet.
No, that's okay. Take your time. Let's give you guys another 60 seconds. Go for it. Do you guys remember that this is based on your absolute temperatures, your Kelvin in this case? You can't use Celsius.
The issue I ran into is whenever I was doing my conversion on my calculator for some reason.
Yeah.
I mean, I know I could have just added 273.15.
Yeah.
But I did -10 and then I hit convert on my calculator and it gave me -283 Kelvin.
Yeah, that
and
is.
I went off of that number because I wasn't using my brain.
Okay, guys, to do this, you need to convert this to, it's roughly 303. It's roughly 303 Kelvin. See, that there is Celsius. And this one here is a positive 263, right?
Yes, sir.
Yeah,
And
15.
for max,
We won't worry about it. Now this equation here, what you got to do is you got to go. See, I forget the equation. Let me think. You got to go T sub L, and you have to divide by TH minus TL. But the TL has got to be in Kelvin. So it's 263. Now the difference, you can do the difference in Celsius, it's 40. Between minus 10 and 30, it's 40. But between 263 and 303, it's also 40. So it doesn't matter about that. And these units cancel. And what I got was 6.5. Can't read my own writing. It looks like 7.5. 6.575 is the maximum possible for that refrigeration cycle. And I'm listening for an uh-huh.
yes, sir.
Yay, there's one.
Okay, I got it.
Good for
Me
you.
too.
Yay. Now notice that the actual 5.2 is smaller than the maximum. That's good. Shouldn't stuff always be smaller than the maximum? It kind of
Yes,
makes
sir.
sense. You don't want stuff bigger than the maximum, then something bad happened. Okay, well, there's a typical refrigeration cycle with the schematic. Now we're going to do an actual refrigeration cycle. And this will take us a while, but it'll be fun. And I need to say goodbye to all of that. We're going to do an actual refrigeration cycle. It's going to be problem 965. Problem 965. Okay. Need a little room here. I'm going to have to say goodbye to all of that. Hope you understood it. I think refrigeration cycles are pretty important. You guys like being cool in the summertime. You like your your air conditioner. You like your ice cream cold or whatever. Now, if you go to 965 and read it, it's in your book someplace, 965. It says R134A. That's what you have in your car. You guys have air conditioning in your car. That's what you have, R134A. Used to be R22A, but they did away with that. But we really need this. We really need this TS diagram. So let me do that. There we go. We're going to do a TS diagram. Now it's R134A. It's what you guys have in your cars. And here's the diagram for it. This starts off as a saturated vapor, and then it goes to a superheated vapor in the compressor. That's your compressor. And then you have an isobaric condenser. See, this is your condenser. And that goes to state 2, to state 3, to the, it goes to saturated liquid right there. See, that's saturated liquid. This is saturated vapor. This is superheated vapor. And then we have your expansion valve. And it's an isenthalpic device. And we draw it with a dashed line. Maybe not that crooked. Oh, well. To state 4, there's state 4. And it's an isenthalpic device. It's a throttling device. See, and now at state 4, what we have is saturated mixture. We have saturated mixture at state 4. And we have our cycle. Notice it goes counterclockwise. It doesn't go around in a nice circle like what we did a minute ago. But it is counterclockwise. Can you see? It's counterclockwise, all right. And you know, this is the compressor, condenser, expansion valve. Now I'm going to need that room there. The expansion valve I think I told you guys this. Maybe I didn't, but my expansion valve went out on my car air conditioner, and it's at a place that's hard to get to. The labor cost was something like, I don't know, $300. The expansion valve itself is very simple. It doesn't have any moving parts. It's just a throttle is all it is. It's a throttle. The H3 is equal to H4, the specific enthalpy. That's the first law for throttles. Well, because it was hard to get to, the mechanic had to take everything apart. It's going to cost $300. So I just said, forget it. I'll just drive this car this summer with my 460 air conditioner. Do you guys know what a 460 air conditioner is? That's when you drive with your 4 windows rolled down 60 miles an hour. That's a 460. Boy, it was hot that summer. It got over 100 for a couple of 3 weeks that summer. I should have gone ahead and had him put that expansion valve in, but too cheap. Okay, now what we're going to do is we're going to make a table, and we're going to fill it in. We're going to go from 1 to 2, 2 to 3, 3 to 4, 4 back to 1. And we're going to put in our pressure, specific volume, temperature, specific enthalpy, specific entropy, heat per mass, work per mass. This is the big plan. We're going to fill in this wavy chart that I'm making here. So what if it's wavy? We're going to fill in this chart for this refrigeration cycle. Okay, now let me read on. We're doing problem, if you just tune in, guys, and somebody new there, got some wonderful people here. Miranda, Ross, Mark. There's a big crowd. We are doing problem 965. It's a refrigeration cycle. It's R134A, and they said the minimum temperature is -10. Well, you know what? That would be the temperature at 1 and 4, wouldn't it? -10. Let's put it in. State 1 is -10. State 4 is -10. And we're talking degrees Celsius, right? We're talking degrees Celsius, yeah. Keep reading. A maximum pressure of 1 megapascal Maximum pressure 1 megapascal. But remember, condensers are isobaric. So the 1 megapascal at state 2 is, I'm going to write it as kilopascals. State 2 and state 3 are both 1,000 kilopascals. That's the same thing as 1 megapascal. Because the condensers are isobaric. Okay, well, great. Let me keep reading. Assume an ideal refrigeration cycle. Find the specific heat. That's what this is. This is an ideal refrigeration cycle. You have an isentrope going from 1 to 2, constant entropy. See it? It's an ideal. In a real cycle, this will edge off to the right just a tad, and it'll be a dashed line because you'll have some irreversibilities. Assume the ideal refrigeration cycle, find the specific, yeah, blah, blah, blah. Okay, we're going to fill in the blanks. Here goes. I think we got all the info. We're going to need our book, though. I hope you have a book or else access to your cell phone or whatever. We got a lot of boxes to fill in. Now, one of these processes is adiabatic. And so one of these Q's is 0. I wonder which one it would be. What do you guys think? Anybody want to take a guess as which Q would be 0 here? 1 to 2, 2 to 3, 3 to 4, 4 to 1.
4 to 1.
4 to 1. No, that's not going to be 0. In fact, this is the reason why we have this air conditioner. There's going to be a Q there from 4 to 1. That's going to remove that heat energy from your ice cream. That's why we have this refrigerator. No, 4 to 1's not 0. Try again. Was that Don?
Yes, sir.
Try again, Don. I mean, you got three chances left.
Well, the only other one that I would assume would be 1 to 2.
Yeah, 1 to 2. Good going. The reason for that is a 1 to 2 is called an isentrope. It's a reversible adiabat. It's a reversible adiabat. There's no heat transfer from 1 to 2, so you get a 0. But now there's another 0. Where's the other 0?
3 to 4.
That's right. I don't know if it's advertised or not, but 3 to 4 is a throttling. 3 to 4 is a throttling. And throttling is also adiabatic. It's not reversible. If it was reversible, I'd draw it with a solid line like these others. But it's not. There's all kinds of irreversibilities in throttles. Hang on. Let me see who wants me. Somebody wants me. Hello? Yes. Yes. Hey, look, I couldn't come last Thursday. Can I come later this afternoon? How late are you going to be there? I'll be there in plenty of time. Okay. And see you then. Thank you, Sean. Bye-bye. All right. Now let's see. Where were we? We're filling in all these boxes. Okay. I told you about the throttling is adiabatic. Yeah, we did that. Now, are any of these little W's 0?
2 to 3 and 4 to 1.
2 to 3 is 0 because condensers don't do any work. You don't have to plug them in. They don't provide you with any work. You don't have to plug them in. And what was the other one? 4 to 1? Is that what you said?
Yes, sir.
4 to 1. 4. That's an evaporator. Let me write that for you. 4 to 1 is an evaporator. It's kind of like boiling. It's an evaporator. Evaporators don't do any work. Now, you might wonder, well, how come? Because there's an area under that. Isn't the area under that equal to the work done? Well, yeah, on a PV diagram with a control mass, but this is not a PV diagram, it's a TS diagram. And if you did it on a PV diagram, it would still be flat and the area is not under it, it's the sideways area. There isn't any, there's no work. There's no work done by evaporators. I think I told you about that on one of our wonderful times together. But there's one more 0. What's the other? There's 3 of these that are 0. What's the other one? There's another 0 in the work column.
It would have to be 3 to 4 because a compressor definitely does work.
Yeah. By elimination. See, a throttling doesn't do any work either. A throttle is just got like a constriction, and it doesn't do any work. So, man, we got a bunch of points right there. They're worth a point apiece on your final, so you might as well get all the points you can. Okay, well, we need to fill in some more boxes here. Anybody got any ideas? I got an idea. You see this state 1 here? That's saturated vapor. So go to your tables and look up -10, but don't go to water. We don't want to look in the water table. We want R134A. So shop around, find R134A. Hey, I found it. Look up -10, R134A. Hey, I found it. And I found the pressure. My book says 201.7. And it also has a specific volume. It says 0.09921. You really need a book or your cell phone. You need to know how to access that for your final exam. You got to have those. I'm going to wait till I hear an for those.
Yes, sir.
Good. Excellent. Now, here's another thought. You got PV and T. Could you use PV equals RT? Could you use PV equals RT?
No, sir.
No, you can't use that because it's not an ideal gas. It's R134A. That's not an ideal gas. It's especially not an ideal gas at state 3. Do you know what it is at state 3?
Saturated liquid.
Yeah, it's all liquid. It's 100% liquid. So you don't want to use an ideal gas law on 100% liquid. No. Okay, well, let's keep going here. Hey, look at -10, we can get the specific enthalpy. It is, and I got lost there. It is a -10. My table here says 392.28.
2.8.
We're doing great. You know, we really need to put the units on here. Let me do that. That'd be good. See, these are kilojoules per kilogram. These are kilojoules per kilogram Kelvin. Kilojoules per kilogram. Kilojoules per kilogram. Okay. Now we can get an S at state 1, too. It's saturated vapor. Specific enthalpy 1.7319. 7319. Hey, we're really making progress here. Look at all those boxes we filled in. Let's go to state 2. Now, what do we know at state 2? Well, we know the pressure, but we know something else. What is the other thing we know?
Saturated vapor. Or, I mean, superheated vapor.
Yeah, it's superheated vapor. So let's go to the superheated vapor chart. I'm going to shop around and find superheated vapor. Well, there it is. And what do
And it
we
shares
want?
the same S value, doesn't it?
That's the dirty little secret. The dirty little secret is this is 1.7319. Because it's, what's the word? Going from 1 to 2, it's an isentrope. It's a reversible adiabat. What that means is S1 is equal to S2. Or in other words, delta S is 0. So, hey, look, we know two things. We know the pressure. We know the specific enthalpy. We can get the rest of it. But we're going to have to go to 1,000 kilopascal. Okay, let me find those. I found it. 1,000 kilopascals R134A. But see, we need 1.7319. 1.73. Uh-oh, we're going to have to interpolate. I don't have room there. Why don't I make some room up here? Let's say goodbye to all this stuff. We don't need it. Okay, we're going to have to interpolate. See, we're at 1,000 kilopascal. Now this is going to be boring and tedious, but I want you to get a high grade on your final. So let's just suffer through this, shall we? Now we need these values here. We need P, V, PVT. Well, we'd like to have all of these, and S. Okay, now I'm going to put them in here. Here goes. Well, we already know. Never mind the P. We already know that. The pressure is 1,000. But the V is 0.02047. And the temperature is 40. And the little h value is 420.25. And the S value is 1.7148. And the next line down is 50. And the V is 0.02185. And the H is 431.24. And the S is 1.7494. But you see, what we want is 1.7319. That's in between those two. We're going to have to interpolate, but we can do it. I'm going to shut up for a minute, maybe two, and I want you to interpolate here, here, and here for me, and I'll put the answers up here in just a minute. On your mark, get set, go. Do you know that black little small backpack that I have on the floor of the garage? You know the little uh, zipper and on the back of it?
Yeah.
The keys are there.
Okay.
Now put it back when you're through. I want to keep those keys or we're in trouble. Okay, guys, I gave you a little time. I bet you got at least one of those. Here's what I think. I think the temperature is 44.94. I think the H is 425.68. 425.68. And I think the specific volume is 0.02115. Now, if you got any of those right, I want to hear an uh-huh.
Yes, sir.
I need another uh-huh.
Yes, sir.
Yay, good. There's another. I need another one more uh-huh.
Yes.
There's another one. All right, now we're going to put these in here. See, this is 0.02115. This is 44.94. This is 425.68. We're doing great. We're filling in the chart. Let's keep going now. Now, this one's going to be easy. State 3, you know where that is? That's saturated liquid. So just go to 1,000. I take that back. It's not going to be easy. I lied. It would be easy if they had a table with 1,000, but they don't. I tell you what they do have. They don't have 1,000. They have 887 and 1017. Okay, now how are we going to do that?
Mr. Griffin,
Yes.
3 to 4 is a, yeah. Is it a thought? Oh, I'm sorry. I think I misunderstood.
That's okay, Coy. Right now we're looking at state 3, and we know the pressure at state 3 is 1,000.
We can get the temperature from superheated vapor.
Hey, now that's a good idea. I like that. That was Don, wasn't it?
Yes, sir.
The temperature is 39.37. Good going, Don. 30. Dawn has got the temperature. It's 39.37. At state 3, because that's the temperature anywhere in here, because it's an isotherm. Good going. But now to get the V, I think we're going to have to interpolate. So go to the vapor dome chart, which they call it the saturated table. And we need 1,000. I don't see 1,000, but we're going to get it. Here we go. I need some room to operate, so I'm going to erase all this stuff. Yeah, say goodbye. I hope you understood that. Now we're going to go to the saturated table, what I call the vapor dome table, and they don't have 1,000, but I tell you what they do have. I tell you what they do have. They have, we'll put your temperature, pressure, specific volume, H and S. I think we need all of those. Now their temperature there. This is ugly. I'm sorry it's ugly, but that's the way it is. It's at 35, isn't it? At 35 degrees Celsius, the pressure is 887.6. Specific volume is 0.000857. I wonder if you guys can read that. It's awfully small. I hope you can read it. And then the specific enthalpy is 249.10. And the specific entropy is 1.1673. And see, what we want is 1,000 kilopascals, but they don't have it. But the next one up is 40 degrees Celsius and 1017.0. And the specific volume is 0.000873. Specific enthalpy is 256.54. And specific entropy is 1.1909. Now what we're going to have to do is we're going to have to interpolate all of that. But we can do it. That doesn't really scare us. It's just a boring, tedious thing. And again, I'm going to shut up. I want you to try to get a couple of those, and I'll put the answers up here in a minute. See if you can interpolate. You get the temperature, the specific volume, specific enthalpy, and specific entropy. On your mark, let's set go.
Mr. Griffin, I have a question.
Yes.
If 4:1 process is like if the temperature doesn't change, like the pressure would be also the same, right?
That's right. Good thinking. Good thinking, Coy. We're going to put a 201.7 right here, and we're going to dedicate that to Coy. I like it a lot. Okay, I'm going to shut up, and you have a minute and a half. See if you can get a couple of those for me. How's this microphone? Let me bother Kristen a minute. Kristen, we had trouble this morning, but how's the microphone doing right now?
It's doing good so far.
So far, so good?
Yes, sir.
Good. And remember, the recording came out perfect. So you can always look at that lecture on YouTube. Okay, well, we probably should move along. I'd like to finish this. I would like to finish it. All right, here's what I got. I got 39.3 for the temperature. Well, 37. Well, we already did that. But if you interpolate, I think I got 39.3, but one of my excellent students went to the superheated vapor table and got it exactly. It's 39.37. You can write it that way if you want. We did good on that. And here's the V. I got 0.000871.
Yes, sir.
Yay, there's somebody. And for the little h, I got 255.6.
Uh-huh.
Let's put that in. That's 255.6. And the V is the 0.00871. 0.00871. And specific entropy. I got 1.1878. 1.1878. Yay, we did great. Well, we don't have much left. What do we got? State 4. Now, what do we know? What do we know about state 4? We know the pressure. We know the temperature.
The enthalpy.
That's correct. We have the specific entropy. This is the dirty little secret of the refrigeration cycle. These two are the same. Going from 3 to 4, it's a throttling. Throttles have the same specific entropy. Now with that, we're going to be able to find these values here. Okay. Dang, we're running out of time here. It's so sad when you're having fun. I need the space. We're going to have to sacrifice all that. But if you haven't learned how to interpolate yet, now would be a good time before the final exam for you to learn how to interpolate. It's got nothing to do with intelligence. I find that some brilliant students they just have trouble interpolating. Okay, here's the dirty little secret to find out these babies here. We're going to use this equation here. This is saturated mixture down here, and we know that H4 is equal to HF plus the quality at 4, HFG. So we're just going to look it up. At minus 10, help me find minus 10. There it is. I found it. And HF is 186.72. First of all, we'll put the H4 down. That's 255.6. And the HF is 186.72. See, we're doing minus 10. If you go to R1 134A and look up minus 10 on the saturated table, you'll find that. We're going to get the quality. HFG is 205.56. Okay, get your calculators out and find the quality at state 4.
got 0.335.
How come I'm getting 0.3397?
I got 0.3351.
Yeah.
Just a minute here. Just one tiny minute. Let me do it. Not that I don't trust you guys. 255.6 minus 186.72 divided by 205.56. 0.3351. Is that what you're telling me?
Yes, sir.
Well, I did this before and I got a slightly different number. I wonder, what did I do wrong? Just a minute here. Let me see here. Okay. Yeah, I see what I did wrong. I see what I did wrong. Auga. You know what it was? It was dyslexia. I reversed a couple of numbers. Here's what I did. I went 256.5. Did you see what I did? I switched a couple of numbers. Did you know that 1 out of 10 people have a little touch of dyslexia? And I'm one of them. So I got the wrong answer. So let's get the right answer. So it's 0.3351. You guys agree now, right?
Yes, sir.
Yeah, good going. So let me get that written down. So that'll make my values slightly different. We'll get the right answers. All right. What we're going to do is we're going to get the V and the S, and then we'll have all of these. So I need this room right here. And there's more than 10 of you guys, so there's probably one of you out there that has a little touch of dyslexia like me. So it's okay. We'll manage. All right, now let's get the S, the little s. Here we go. Little s is going to be at minus 10. We have to look it up now. It's going to be 0.9507. Plus the quality at 4, which we have. We did it correct. Times 0.7812. And we're going to get our little s. Here goes. We're doing it. I'm getting, for state 4, 2.2365. So that goes right here, 2.2365. I hope somebody got that. Anybody get that? I could be wrong. Maybe I should do it again.
I got 1.213 twice.
Yeah, I'm not.
You're right, and I am way off. Something bad happened. Let me do it again. But I think I have the right numbers there.
You do.
Those are the right numbers. Let me try it again.
Yeah, you made me second guess myself, so I reran it.
Yeah.
Well, I'm trying to build up your confidence level, and this ought to do it. It's 1.212 for something. So this was wrong. Don't you feel better now? 1.2125 maybe. There we go. That what you get?
Yes, sir.
Yay. All right, well, let's get this little v here.
Yeah.
And here we go. We're going to get little v. Now, this is going to be little v4. And what that's going to be is, got to shop around here again, 0.000755. 0.000755 plus the quality of state 4 times 0.09845. 09845. All right, we're going to get the specific volume at 4. Here goes. 0.000755 plus 0.3351 0.09845. Ta-da! 0.03375.
Sure.
Yay! 0.03375. Now we filled all these in. All we got to do is these little boxes here.
I have a question, sir.
Yeah, go ahead.
I know it's probably a dumb question because it's the ideal refrigeration cycle, but
Yeah.
is it a reversible cycle even though it has an irreversibility in it?
It is not a reversible cycle
Okay.
because it's got the irreversibility of that throttling,
Throttle.
that expansion valve thing. Okay,
So
well,
it's gonna have S generated.
yeah, it's got S generated. It sure does. Okay, now we got to fill in these 4 boxes. How are we doing on time? Oh, gee, it's sad. We're kind of running out of time. But I haven't given you any homework. All right, here's your homework, guys. Let me write this down. Just a minute. Let me get the right numbers on here because I got the wrong numbers. This is 03375, and this is 1.2125. And so that's going to change some of my answers. Okay, now here's your homework. There's a little room right here. Your homework is to finish, I bet you can do this, finish this 965. In other words, you've got, well, gosh, there's only 3 boxes. There's only 3 boxes. You should be able to get that. That's going to be your homework. Finish this 965. Now this is not to turn in. Not to turn in. I'll give you some more homework before we're through. You know, there's not much school left. We're going to have a wonderful lecture on Thursday. And then next week we'll have Tuesdays and Thursday wonderful lectures. That's it. That's it. And I'll give you a nice take-home final. And we'll be done, done. Okay, now finish that. Don't turn it in, finish it. And we'll do it. We'll give you the answers tomorrow. Now here's where we're headed. Now, let me tell you what we're going to do next. We need a little room here to write. Don't have any room to write. We'll write it up here someplace. Here we go. The next thing we're going to do is the auto cycle. spelled Otto, O-T-T-O. That's not a pie. That's two T's. O-T-T-O. It's a theoretical cycle for the automobile engine. And then we're going to do the diesel cycle. And I know you've heard of diesel engines before. And then we're going to do the Stirling cycle. We got 3 more cycles to do. And then we're going to be done. Now, I'll tell you the cycles we've done. We've done Carnot cycle, Rankine cycle. Today we did the refrigeration cycle. Then we're going to do these 3 cycles. And it's sad, but we're going to be done. That's where we're headed. You could read about the Otto cycle if you wanted to, but we'll cover it on Thursday. Go home and go home. Go home. You're already home, right? Finish this. This is your not to turn in homework. Is there any last comments or questions?
No, sir.
Okay, well, I'm going to.
I have one, sir.
You go ahead.
The 106, 106 E is due tonight, right?
Yeah, it's due tonight. You're right.
It's
And
not late yet, right?
a lot of people have already done it, but turn it in. Now,
Thank you.
try not to be late because I'm going to be grading all of those. I've graded a lot of people. A lot of people did real good on it. And some people got a 3 because they did something bad. Okay, anybody else?
So when will you start putting like all of our homework and quiz scores onto Blackboard that were from before what we started submitting on Blackboard? So basically everything up until the last problem. When will you start putting those in? So just like, I'm just curious kind of like where I am and stuff.
Tell you what, let's do. Let's give you 1 or 2 more homework assignments that I'm going to grade.
Uh-huh.
And then I will total up your homework and quiz grade and post it for you on Blackboard.
Okay, so it's not going to be until next week then sometime?
Yeah, it'll be next week sometime.
Okay. I was just curious. I just kind of wanted to see where I was to see.
Right, I don't blame you.
I have a question.
Yeah, go ahead.
Are we turning in the homeworks for 749, 792 that we did?
Let me look and see, just a minute. 749.
I think that's right.
749.
There were 2 chapter 7 homeworks that I remember doing that I wasn't sure. 759, sorry, 759 and 792.
Oh, 759.
I think those were don't turn ins, if I remember right.
Those are just done because we love to do them.
Okay.
Yeah. And I was still learning how to grade homework, but I'm catching on. Anybody else? Maybe we'll just have 1 more graded homework because Kristen wants her total, and I don't blame her.
Yeah, I just need to see how bad it is going into the final.
Right. Well, maybe it won't be as bad as you think.
What kind of stress level we need to enter the final with?
Yeah, exactly. That's what I like to know. Like, what stress level am I entering the final with?
How do I prioritize my classes to see what I study more?
Yeah, that's right.
Exactly.
Right. I'm with you. Any other last words or comments? Okay, well, I'm going to quit for now, and I will see some of you in the morning, I guess.
Yep. See you in the morning, sir.
See you in the morning. Bye-bye for now.
Bye.